Hello, my name is Samuel Alvarado. This is my exploration of the nature-inspired heuristic algorithms for our project for Summer Intercession 2026. Here, we'll be going over some of the nature-inspired algorithms and kind of go over how they're approached to solve complex scheduling problems and going over kind of some of the applications that they're used for throughout the industry for some common applications and then some more specific applications. So let's get into it. The first optimization or algorithm that we're looking at here is the ant colony optimization, which is inspired by how fast ants find the shortest path to food using pheromone trails. So an example of this that I like to think of is you leave some sugar on the table, maybe a popsicle or something. You walk away, maybe see an ant, and a couple minutes later you come back and there is a army of ants all swarming towards the food. That is because the ants use pheromones to signal to other ants this is the path to take to find the food. So in this algorithm, the better solutions will attract more attention while weaker ones fade over time. Some examples that I saw during my research is that this has been applied to surgery scheduling, helping allocating resources like staff and operating rooms and stuff like that, specialized equipment. And it helps reduce the delays and minimize, the total project time, or in this case, the make span, which in this scenario was the total time of all surgeries being collected. It's also utilized in manufacturing to improve job scheduling by filtering out what is the strongest path and then signaling out to the algorithm what is the most efficient path. The next algorithm we have is the firefly algorithm. The thinking here is that a firefly will attract weaker fireflies if it is brighter, therefore bringing in the fireflies, or in this case algorithms, closer to a better scenario. So the stronger a scheduling or solution is, the more it will attract and gravitate other solutions to start going that same way. But there is still the randomness calculated in with the coordination. So it's not a completely linear path. It allows for exploration. So some applications that I saw were disassembly lines. This was used to take into account all the different factors and try to reduce cost, idle time, and total make span. Also used for medical field. I think this is more specifically for bone marrow applications, which is really cool. And it's not necessarily diagnosing the patients or anything like that. It is calculating what softwares are putting out more efficient diagnosis. So it's looking at the system of the diagnosis itself. Also, this is used for transportation systems, such as, what would be fastest, air, water, or road travel. It takes into account all these in an algorithm per se, and will output the one that is most efficient for cost, time, scheduling. Next one we have here is the gray wolf optimization, which is based off the leadership hierarchy of wolves, such as the alpha, beta, and other ranks. So when the algorithm is using a gray wolf optimization, the best solution outputted will be considered the alpha, and the other options will be allocated as so, and the lesser options will be guided by that alpha to kind of move towards a stronger solution. This algorithm hopes to explore multiple options while still focusing on the best one, keeping that one in mind. Applications that I saw were applications including improving power grid efficiency, optimizing industrial processes like drying silica powder materials, and helping with construction resource leveling by balancing labor and equipment usage to reduce unnecessary tasks that didn't have high critical importance, and we're able to allocate those later to the job to make sure the most important task got done first. This next algorithm is probably one of my favorites because frogs is one of the most interesting animals in my opinion. The shuffled frog leaping algorithm is inspired by how frogs will hop around and look for food in groups. And between these groups, the frogs, or solutions in these cases, will share information between groups, allowing the weaker solutions to learn off the stronger solutions and eventually come out with groups that are strong and have learned from other ones. So this will be applied towards algorithm and solutions that are outputted. The weaker ones will be learning from different groups of stronger ones and improving, so on and so forth. Poor performing groups may be calculated to have to restart to avoid getting stuck in bad groups and coming out with poor solutions. This algorithm was used in fabric production to reduce delays, and in manufacturing to handle disruptions, kind of emergency situations. What is the best case scenarios for responses to avoid extended delays, and in airport scheduling to optimize planes, earliest time planes are landing, the most common time, and the latest time. The frog algorithm will look at all those times for planes and kind of output best and worst case scenarios and try to find the best solution possible. The next algorithm that I chose was the bat algorithm. It's based off how bats use echolocation to find their food, and the louder the echolocation for the prey in this case, or the best solution, will give a stronger signal to other bats to indicate where the prey, or in this case for the algorithm, what is the best solution. So as better solutions are found, they produce stronger signals that will guide the algorithm to other solutions to move in the same direction. The algorithm will also include adjustments to avoid early convergence and encourage continued exploration, so there's not stuck in a bad path. What we saw is that it was used in cloud computing to reduce cost and processing time, to allocate resources for computers such as CPUs and stuff like that, and in energy systems for power grids to see when is the best time, for all the different options. So for example, for this one, in the case of power, towards noon, probably kind of up the requirements for solar and reduce your demand on the electrical grid by optimizing that solar power at peak solar times. At first, these algorithms, to me, they seem very similar. They all might kind of seem repetitive at first, but that is because they're all trying to find the best possible solution. That's what they're all aiming for. Every one of these algorithms has a unique characteristic based off their, natural inspiration. Some focus more on exploration and linear, and others will focus more on randomized exploring. Others on hierarchy groups or group learning, but all work towards improving efficiency in all types of complex systems. In conclusion, the nature-inspired algorithms, provide powerful tools for solving complex issues across all kinds of industries by mimicking behaviors that kind of evolved in nature, such as cooperation, adaptation, and the competition. These algorithms effectively are able to process large amounts of data and find better solutions. So while they all share the same goal and try to get the same output, their processes are different, and based off the problem at hand, they become more suitable for different types of problems. Overall, these methods show how studying the natural system, kind of what nature's evolved to, can lead to smarter and more efficient engineering and scheduling solutions quicker. So yeah, that is my presentation here. So thank you.